Hello everyone. In this video, we are going to look at the example of coaxial cylindrical capacitor as a solution to Laplace equation for one-dimensional potential function. In this case, we have considered a cylinder of radius A, which is having same axis with another cylinder of radius B. We are considering the region between the two cylindrical surfaces are separated by an insulating material whose dielectric constant is epsilon r. We consider the length of both the cylinders as L, and the area of the cylinder, surface area of the cylinder, can be estimated from the radius and the length. So the area can be given as 2 pi into rho L, where rho is equal to A for the inner cylinder and rho equals to B for the outer cylinder. We know B is greater than A in this case. We are going to consider the Laplace equation for this case to solve for the potential function. When we consider the potential between the two cylindrical surfaces, it is a function of radius. So we know the function of radius is a one-dimensional potential function, and the region between the two cylinders is having no charges, which is a dielectric material. Therefore, we can apply the Laplace equation for the charge-free region between the two cylindrical surfaces to get the potential function. And from the potential function, we can find electric field intensity as negative gradient of potential. And from electric field intensity, we can get the expressions of electric flux density in terms of epsilon. And by applying Gauss law, we can find charge from the electric flux density. From the charge, we can find the capacitance of this cylindrical capacitor by taking ratio of charge stored in either of the plates divided by difference in potential between the two plates. These are the steps which has to be followed to find the capacitance of the cylindrical capacitor. We will go through the steps one by one. Let us consider the two boundary conditions by applying the potential as given. In this case, the outer one we are considering grounded, and the inner one is connected to the positive of the supply voltage, which is V0. With this, we can write the boundary conditions as at radius A, the potential is positive V0, and at radius B, the potential is 0. These two forms the two boundary conditions to solve for the second order differential equation, which is the Laplace equation. We have to consider the system of coordinates as cylindrical system. We will be writing del square V equation in the cylindrical system as here. And we also know the potential between the regions of the two capacitor plates is a function of only variable rho. In that case, differentiation with respect to rho and differentiation with respect to z can be 0. And we have only this function, which is a differentiation of rho twice. This can be written in terms of ordinary differentiation. Since b is a function of only rho, no need of partial differentiation. We can write this as ordinary differential equation. This has to be solved by integrating twice with respect to rho to get this potential function v, which is a function of one dimension, which is rho. So before doing the integration, we have to rearrange these terms. So when we consider this 1 by rho, which is in multiplication with the differential elements, this can be made to the right-hand side. Multiplying this with 0 will be 0, and you'll be left with the differential terms alone in the left-hand side. D by d rho of rho dv by d rho equals to 0. Now, to eliminate this differentiation, we will be performing integration with respect to rho for this equation. So integration will remove this d by d rho, and in the right-hand side, we have 0. Integration of 0 will be 0. And there are no limits provided, so that has to be written in terms of integration constants. So 0 plus C1 is the right-hand side. And in the left-hand side, this integration with respect to rho cancels one differentiation. You'll be left with rho dv by d rho in the left-hand side. So now this rho again has to be moved to the right-hand side, which will give dv by d rho in the left-hand side equals to C1 by rho in the right-hand side. Now we can perform integration one more time with respect to rho to get the potential function v. So integration of this will remove the second differentiation with respect to rho. And in the right-hand side, we have C1 constant and 1 by rho d rho we have to be integrating. So left-hand side will be v, and integration of 1 by rho d rho will be logarithm of rho, natural logarithm of rho. since no limits are provided, we should consider integration constant for the second integration with respect to rho. So thereby we get the potential function V as C1 logarithm rho plus C2, where the C1 and C2 are the integration constants which can be found from the boundary conditions which we have. So we can consider the two boundary conditions. By applying one boundary condition, we will get the equation as at V equals to V naught, rho equals to A. So we will write V naught equals to C1 logarithm A plus C2. Applying the second boundary condition, we will get 0 equals to C1 logarithm B plus C2. Now these two are equations we have. We know B value is greater than A. We should rearrange the terms in such a way that B is greater than A. And solving these two equations, we will get the constant C1 and C2. By taking the second equation, rearranging the terms, we will get C2 is minus C1 logarithm B. Now, by taking the first equation, we can write V naught minus 0. So, when you take these two equations, V naught minus 0 equals to C1 logarithm A minus C1 logarithm B. Now, subtracting these two equations, we will get this equation. When we consider this, A is smaller and B is larger. So logarithm B minus logarithm A we should write. So when we rewrite this as logarithm B minus logarithm A term, one negative sign should come in the left hand side. So thereby we will get C1 logarithm B minus C1 logarithm A equals to minus V naught. We know logarithm B minus logarithm A can be written as logarithm B by A. We can write this for C1. So C1 can be written as minus V naught by logarithm B by A. Now applying the C1 here, we can write the C2 value also. So C2 can be written as V naught logarithm B by logarithm B by A. So instead of C1, we can write this, multiply with logarithm B, and one negative sign and negative sign will be cancelled. We'll get C2 as V naught logarithm B by logarithm B minus A, and C1 is minus V naught by logarithm B by A. By applying these two, C1 and C2, into this expression, we will get the potential V as a function of rho. So V, which is a function of rho, can be written as C1 multiplied with logarithm rho. So this has to be multiplied with logarithm rho and C2. So we will be getting V as a function of rho as given here by this expression. Next step is to find electric field intensity. So from this potential function V, which is a function of rho, in cylindrical system, we have to estimate electric field intensity, which is negative gradient of potential. We will be writing the formula for del V in cylindrical system. And we also know V is a function of rho only. So there are no phi variable or z variable in this. So when we try to differentiate this with respect to phi or rho, that will become 0. And we have to take only differentiation with respect to rho. This has to be differentiated with respect to rho. When you take the first term, differentiation of this is going to give constants V naught by logarithm B by A are constants, and differentiation of logarithm of rho will be 1 by rho. And the second term is all purely constants. Differentiation is going to be 0. So this is the differentiation of V with respect to rho. When you take this differentiation of V with respect to rho, we will get this expression. Now, the next step of electric field intensity calculation is minus del V. That is going to give minus of this minus V naught by logarithm B by A into 1 by rho, and the corresponding direction vector for the first term is A rho cap. So the negative of negative will become positive. So this is the expression for electric field intensity, which is V naught by rho into logarithm B by A. The direction is A rho cap. The unit is volt per meter. The next step is to be finding flux density vector D, which is epsilon times E vector, where epsilon is epsilon naught multiplied with epsilon r of the region separating the two capacitor plates. Multiplying this with epsilon naught epsilon r, we'll get the flux density vector D, whose unit is coulomb per meter square. Next, we have to estimate the charge from Gauss law, which is surface integration D dot ds. Now, considering this D, we have to perform surface integration over the cylindrical surface. And we also know the cylindrical surface integration gives the surface area of the cylinder, We can either perform integration with proper limits, or if we know the surface area of the cylinder, we can write it directly. This shows how to integrate for the surface with variables phi and z, and the surface element is rho d phi dz. We have to perform integration for phi from 0 to 2 pi and length is 0 to L. Thereby, we will get the surface integration ds is 2 pi rho L. So wherever we have the surface integration ds with the constants in multiplication, we can write the surface area in terms of this surface integration. When you look at this integration, these are all constants which can be taken outside, and you'll be left with surface integration ds, and that surface integration ds has the value 2 pi rho L, which is the surface area of cylindrical surface whose radius is rho and length is L. So we can write this constant in multiplication with surface area of the cylinder, which cancels the rho from the terms here and gives the charge enclosed as 2 pi epsilon naught epsilon r L into V naught in the numerator, and divided by, in the denominator you have logarithm B by A, which is the charge stored in each of the plates of the capacitor. Here the cylindrical plates is considered. The unit of charge is coulomb. Now from this charge, we have to find what is the capacitance. We know the formula for capacitance is charge stored in either of the plates, the inner plate and the outer plate. When you consider here, the outer plate is going to be charged to negative potential and the inner one is charged to positive potential, whose magnitude of Q we have already estimated, which is 2 pi epsilon naught epsilon r L into V naught by logarithm B by A. So this has to be divided with the difference in potential. We know the outer one is at 0 potential, inner one is at positive V naught potential. So the difference VD will be V naught minus 0, which is V naught is the difference in potential for estimating the capacitance. So Q divided by difference in potential will cancel out this V naught, and you'll be getting the capacitance for cylindrical capacitor as 2 pi epsilon naught epsilon r L divided by logarithm B by A, where L is the length of the capacitor and B is the outer capacitor's radius, means outer cylinder's radius of this capacitor, and A is the inner cylinder's radius of this capacitor. And the unit of capacitance is given in terms of farads. I hope you have understood this derivation of finding capacitance of coaxial cylindrical capacitor. Thanks for watching the video.